And welcome to the second day of this training course. So I think we can start with the presentations and questions and answers later on according to the agenda. Vladimir, are you ready with the presentation, or who will start today?
Yeah. Can you hear me?
Yes, I can hear you.
Yes, I'm ready. I will start the first one, and then the second one will be given by Igor.
Okay, thank you. So let's start.
Okay. Okay. So if you can see it, good morning and good afternoon to everyone. And the first lecture will be introduction lecture for verification, and it is planning and preparing for verification of diagnostic assays for infectious diseases. So give me a few minutes to present highlights from yesterday. Just to remind you, yesterday we were talking about validation, and shortly it is process when we are making sure that a new product is fit for the purpose. It was an example of the airplane. So don't use term validation if you are introducing already existing methods to your lab. Then we were talking about verification. In short, it is checking if we use the validated product properly. So does it work as we expect in our hands? Then use term verification if you are introducing existing method to your laboratory. Yesterday we were also talking about qualitative diagnostic assays and quantitative diagnostic assays. As we said yesterday, qualitative diagnostic assays, they give only positive or negative result. On the other hand, qualitative diagnostic assays like ELISA and real-time PCR, they give us a numerical value. So analytical laboratories, they usually express it as a quantity, and diagnostic laboratories, as we usually express this numerical value as a positive or negative sample. So in these lectures, we are focusing on quality diagnostic assays with translation of the results to a positive or negative. So yesterday we also concluded that validation is very extensive process. On the other hand, verification reflects validation, but only in a limited extent. Yesterday we have shown it like a mother validation and a child, which is verification. Validation is of a general importance. So it means that the designer of a diagnostic method or a kit shows that it is fit for purpose for any laboratory. Because of that, there are plenty of standards, manuals, and guidelines how to do validation and what validation standards must fulfill. In contrast, verification is of particular importance, for the laboratory where verification is conducted. Because of that, there are only few guidelines available. And a lot of people find it as a problem because they don't know how to do that. On the other hand, we can see it as opportunity because it is up to you.
Vladimir, sorry.
Yes.
Vladimir, I think your screen is frozen. Can you please switch off the sharing and then switch on again?
Okay. How you see it now? Is it okay?
Yes, it should be okay. Validations vs verifications is the slide.
Yeah. Have you seen previous slides?
No, it was frozen on the first slide only.
Okay.
I'm not sure if it was frozen for all, but it was frozen.
Okay.
Maybe you go. You go rapidly through the first slides again. I'm not sure if the others could see everything.
Okay, yes.
I'm sorry, Vladimir.
Yes.
I think maybe it's better if you press F5 or make it as a slideshow, so it's bigger also.
Yeah, let me see. Okay, is it okay now?
I think it's opening. Just a second. For us, it's not yet a slideshow, but I see that in your screen is opening up, right?
What I see now is the full screen mode. So I can try it again. So let me know when it is okay.
It is still not in full screen. It's just a presentation, just a slide within PowerPoint.
Okay, let me close it. Is it okay now?
Yes, it looks okay now.
Yes, that's good. Thank you.
Thank you. Sorry for the inconvenience. So let's go again very fast through first few slides. Highlights from yesterday. We said that validation is indeed making sure that the new product is fit for purpose. So we use it validation only when something is designed for the first time. And we don't use validation if we introduce in our laboratory already existing method. On the other hand, verification is checking if we use correctly validated product in our laboratory. So we use term verification when we introduce already validated method. It's important to talk the same language to understand each other. Also, yesterday we have mentioned qualitative diagnostic assays which give us positive or negative result exclusively, but also qualitative diagnostic assays which give as an output numerical value. So numerical value can be expressed as quantity, and usually analytical labs express it as quantity. Diagnostic labs, they usually express it, that numerical value, as positive or negative. These tests, qualitative, are mainly or mostly used are ELISA and real-time PCR nowadays, and we are focusing on these lectures on ELISA and real-time PCR as quantitative diagnostic assays, which finally give us a conclusion: is it positive or negative? So also yesterday we mentioned that validation is very extensive process and takes a lot of time, a lot of efforts, a lot of expenses. On the other hand, validation verification reflects validation, but only in a limited extent. So yesterday we showed that validation is a kind of mother and verification is a kind of child. Verification is following mother. Again, validation is of general importance. It means that newly designed diagnostic method or diagnostic kit must be fit for purpose for all laboratories that want to use it. And because of the general importance, you can find plenty of standards, manuals for validation, guidelines for validation. On the other hand, verification is of particular importance. It is important for your laboratory because verification is valid only in your laboratory, your verification. Because of that, there are only few guidelines available. And that's the reason why IAEA and Ivancho came to conclusion that we need to give training on verification, how to do that. And a lot of people find this lack of guidelines.
Sorry, Vladimir. Sorry, it's again frozen. It seems this slide is critical.
Okay, let's jump to the next one.
Yes, now it moves. Yeah. Okay.
Okay. So what I was going to say is that a lot of people see it a problem because there are not enough guidelines for verification, but we can see it as opportunity because if there is not something prescribed, then you have flexibility to do what you consider it is important for your laboratory. For example, in the ISO norm, it says that laboratory shall verify that it can properly perform methods before introducing them by ensuring that it can achieve the required performance. So the required performance for your given needs, for your scope. So this is an example. So if you will buy a car, and let's put two questions. What do you need of that car? So do I to perform for verification in your laboratory? So to summarize, according to all guidelines, what minimum parameters should be to consider if we want to verify a quantitative method like ELISA or real-time, in case the output, the final result will be qualitative result, positive or negative. So initially for verification, we have to run analytical sensitivity, analytical specificity, repeatability. It is similar to accordance. Accordance is usually used for qualitative methods. Then reproducibility. Similarly, you can find it as a concordance. Then uncertainty. That's initially what you have to consider. Once you did verification and start using your testing routine work, then ongoing verification should include robustness monitoring and proficiency testing, just to see are you still working properly with your verified method. So each of these methods will be covered in following lectures, so I will not waste time here on this. This repeatability and reproducibility, once we have conducted, we can see from this result what is our initial determination of accuracy and precision. I think yesterday you have heard about accuracy and precision, and we will talk the next days also again on accuracy and precision. Also on ongoing verification, robustness monitoring also gives us information about continuous determination of our accuracy and precision. And finally, when you conduct repeatability, the results can be used for calculation of the uncertainty of our method. Shortly, initially we have the minimum what we have to do is these four things. It's analytical sensitivity and also specificity, repeatability and reproducibility. So are we now ready for verification? It is very important to keep in mind that good planning and preparation is a key for successful verification. If you prepare, if you have good preparation, you have done at least half of the work of your verification. So what should we consider when we prepare for verification? Of course, only if an appropriate validated method is already available. So we have to think, do we have the same matrix to analyze? So if the method is validated for example, on serum, And if you want to test it on for example, some other fluid, then you have to see, are you using the same matrix? Sometimes some matrices, they need additional step for nucleic acid extraction. So you have to consider that depending what are you using, what's material you are using. For example, skin is sometimes very difficult to isolate nucleic acids from skin. The second thing is check your possibility to introduce the validated method without changes in your laboratories. So to do it exactly as it has been done in the laboratory where the test was designed. So the first question then is, do you have all the equipment? Thermocycler, ELISA. I put some asterisks here because I remember in our laboratory we had very good ELISA reader, but it didn't have a filter with specific optical density, specific number of nanometers, and we purchased a kit and we couldn't read that kit on our ELISA reader. Similar can be with thermocycler because there are many models with different specifications available on the market. So if you do not have the same equipment, consider introducing the same equipment. If not, check to be sure that you can test the method on your existing equipment. Then check, do you have all chemical needed? If don't, consider what chemicals are mandatory for the first test to start your verification. Then think, can you achieve the result by modification or adaptation? So just consider, maybe it will not work if I do this, or maybe it will work if I change just this. Again, if we are talking about chemicals, then a price can be quite a reason for modification, because some reagents are expensive, others are cheaper and maybe easier to obtain. But then again, think, will they work or not? Then the next thing is check the availability of positive and negative material. It was already mentioned, it can be reference positive material, certified, secondary reference material, also other positive samples from the field. You probably have a sample bank, you are probably storing some interesting positive samples. So these samples also can be used for repeatability testing, for example. One good idea is also a vaccine. For example, in our laboratory for Newcastle disease testing, limit of detection, we used vaccine in which, live vaccine in which we knew exactly what is the titer in embryo infectious doses. So we did serial dilutions, so we compared, and we could see that our method can detect up to 0.7 embryo infectious doses. Also, think about spiking of your material. So if you don't have positive samples in your sample bank, then you can take a negative sample and you can spike it with the reference material or secondary material. Also, there was a question about synthetic positive controls used for verification. Then, if you don't have any other options, you can also use synthetic DNA because it is easy to obtain that. But there are some disadvantages. For example, if you are working with RNA viruses, then DNA does not take part in all the steps of RT-PCR It just takes steps in PCR, so you don't know is reverse transcription done properly or not. And the second thing, it is best to start your testing from starting material. It means before nucleic acid isolation. So it is better to have original material than to have a synthetic construct, but if you don't have any other options, then you will choose synthetic DNA. Then pay attention and document all the changes you have to consider regarding the original validation process in your verification. For document, I have a different ELISA reader, or I use a different polymerase, or I use different that. Document all these changes in your when you plan to do your verification. Then select the parameters which you have to verify. We have already said a few words about that. And also become familiar with definitions. Know what is sensitivity and what is specificity, not to be confused. Then again, what is analytical sensitivity and what's the difference between analytical sensitivity and diagnostic sensitivity? The same is analytical specificity and diagnostic specificity. Then what is repeatability and what is reproducibility? Then again, what is accordance, concordance? Become familiar before you start your verification process. And then this is in bold. This is set up a verification plan. This is the most important. You have to write a good verification plan. Draft a version of the method as it will be performed in your laboratory in the future. Write down the persons who will perform a validation test. Also fix the number of experiments. Is it 5 repetition? Is it 10 repetition? Is it 20 repetition? How many replicates? Few or more? Then fix the date of experiment. Fix it will be done from that March to that March. Then put a deadline for writing the report on your verification. After you put this on paper, you can calculate the costs of verification and then make sure that your plan will be approved and signed either by quality manager or laboratory head or institute director. Then if it's approved, it means that you have right to do that, and they will not put questions on how much it will cost once you already decided to start. Also, when you writing your verification plan, make sure that some words like replicates and repetitions are analogous. It means maybe you can write replicate. It means aliquot of the same sample, and repetition, it means repeating testing of the same aliquot or something like that. Maybe in your language you have more precise expressions, but be sure not to have confusing words in your verification plan. And what we also have mentioned, make sure that each replicate is tested from the beginning. Don't extract RNA or DNA and then make 2 replicates on the same RNA DNA extract. So start everything from the beginning. It is called, it is important when we will determine measurement uncertainty from top-down approach. It means that we want to include in our uncertainty everything what can contribute to that uncertainty. Finally, the verification plan should reflect the anticipated validation report. They are very similar. On the plan, you write what you will do, and later on the report, you write the same items, but what you achieved in your verification plan. In your plan, you will also put the calculations that you will use to find all the verification data you need at the end. Then documentation, also very important. Document when did the verification was performed, who did verification, who did what, who did this and who did that, by using what, which material, which reagents, which equipment was used, and which methods were used, and why exactly these methods were used. Document and keep the documentations, because if you didn't document, it means that you have not you didn't do that, you have not done it. So keep all the records, write everything and keep all the records. So that was an introduction, and in the next presentation that will give my colleague Igor, you will hear about analytical specificity and sensitivity, and thank you for your attention.
Thank you, Vladimir. Do you have any questions, dear participants? If you have questions, please put it in the chat. Well, no questions so far. Let's proceed to the next presentation.
Okay, good morning to everyone, or good afternoon. We'll continue with the second presentation for today shortly. Just let me try to share the screen. Can you see the slide, or you see the presenter's view?
Yes, it's okay.
It's okay?
Yes, it's okay. Igor, you can start.
Okay.
Okay.
So today we will continue with the description or explanation about analytical assay performances. So as my colleague Vladimir previously mentioned, the veterinary laboratories are required to accredit the methods they use in their laboratories. And what are the requirements regarding the introduction of new tests according to ISO 17025? It says that when the customer does not specify the method to be used, the laboratory shall select an appropriate method and inform the customer of the method chosen. And what it means by an appropriate method, so the appropriate method should be the method validated for intended purpose of use. So another, in the point 7215, it says that the laboratory shall verify that it can properly perform methods before introducing them by ensuring that it can achieve the required performances. So when we talk about verification of existing assay, or when the laboratory wants to introduce in their program of testing the verified already existing assay, it will require a so-called in-house validation. So the existing assay in this context should be the validated commercial kits, like the ELISA kits, with provided validation data by the manufacturer, or mostly in case of nucleic acid detection assay or PCRs, the candidate essay is published in a reputable peer-reviewed journal with inclusion of all required validation data that we need. So before we implement the methods, or before how we will decide what we should do, either validation or verification, we should review the available validation data of these commercial kits or ready-to-use kits, and to identify whether all performance characteristics are determined. So in case the relevant performance characteristics are not available in the documentation that we have, then the laboratory should perform validation. If there are only few, let's say, characteristics or data for specific characteristics available, then it is this interim or middle or doubtful zone where we will need to decide as a laboratory what we will perform, whether we will perform verification on the data available and perform, if possible, a limited validation on the missing data. And it's the easiest part. If we have all relevant performance characteristics available, provided from the manufacturer of the assay that we want to implement in our lab, then the laboratory will need to do only the verification of the performances of this assay in their laboratory. So when we want to verify the existing assay, what needs to be done? Actually, this table summarizes some of the performance characteristics we need to check and compare the necessity of these characteristics, assessment of these characteristics during validation and verification. And we should generate evidence that the performance characteristics like accuracy or precision of the validated assays are comparable when assay is used in another laboratory. So in today's presentation and today's talks, we will focus more on the limit of detection and sensitivity and selectivity of the assays. So what about analytical specificity? We say something about this in yesterday's talks, and the analytical specificity is defined as the ability of assay to differentiate the targeted analyte, like antibody or different organism or different genomic sequences of organism, from non-target analyte. So competing non-target microorganisms, impurities, or matrix components. So in other words, the ability for measuring only what is intended to measure, free from interference which could lead to an incorrect results. So interference from all other competing microorganisms or impurities or other components in the matrix. So for the analytical specificity, evaluation is qualitative, and it should reflect the intended purpose of the assay and whether the assay is designed to be selective, exclusive, or inclusive. So we said previously that during the validation, during development of assay, we need to specify for which purpose do we develop and optimize our assay. So these components, these characteristics could vary in different assays, but nevertheless, they will be fit for the purpose of the original development strategy. So let's just explain or try to describe some of these terms. For example, selectivity refers to the capability for accurate quantification of targeted analyte in the presence of interference such as impurities, matrix components, and degradants. So this is the ability of the assay to target what is the primary goal of this assay to target. So to distract all other possible interference from the background. On the other side, inclusivity of the assay is the capacity of the assay to detect several strains or serovars of a species, several species of a genus, or a similar grouping or closely related organism or antibodies thereto. So, unlike selectivity, in which we assess the ability of assay to detect exactly what it is intended to select, in this inclusivity, it means that it is the capability of the assay to detect several strains of several species, and usually we would like to assess these characteristics in assay which are used for screening. So to cover the wide range of variability within one certain microorganism or pathogen. On the other hand, exclusivity is opposite of inclusivity, and it is the capacity of the assay to detect an analyte or genomic sequence that is unique to a targeted organism and excludes all other known organisms that are potentially cross-reactive. And this characteristics is usually assessed and should be high in the confirmatory or in the differentiating methods. So, for example, if we take the example of real-time PCR for avian influenza, for example, detecting the matrix gene of avian influenza virus would mean the inclusivity of the assay, which will cover all known H or N types of avian influenza. And for the exclusivity, we, for example, we construct the PCR assay, which will specifically, let's say, target the H or N gene, and specifically for the different H types, and will not cross-react and will not produce positive results in the presence of another H or N type, for example, of the avian influenza virus, even though they might be present in our sample. So, in a serological assay, to perform this assessment of the analytical specificity, we need to construct a panel of samples of this, and in this sera, this panel should compose the sera from animals known to have been infected to all species or strains that this test should detect. So this will include the test selectivity and inclusivity assessment. So another type of samples are sera from animals infected to related pathogen, which cause similar clinical symptoms and may cause cross-reaction. And this will test the exclusivity of the assay. And ideally, samples should be selected from animals of known status, as we said previously, the referent animals, and these referent animals can be non-infected and non-vaccinated animals, so the negative animals, non-infected but vaccinated animal, infected, non-vaccinated, and infected and vaccinated animals. So wherever possible, we should provide in our verification and validation, of course, reports, we should provide the details of the source of material. So like blood species, the breed, the age, the sex, vaccination history, the herd history, experimental or field infections, clinical signs if present, and other parameters. And the panel of samples that should be constructed and should be used for nucleic acid detection assay should contain well-characterized isolates of the targeted pathogen, including isolates from a variety of geographical areas and hosts, which will test, let's say, the specificity of assay detecting the same pathogen, but which may have certain, let's say, specificities if originated from a wider range, and this will confirm if the assay detects all of these samples positive, it will confirm the validity of the assay to detect this certain pathogen. And also, it should contain samples of related organisms and pathogens which can cause similar clinical symptoms. So just to exclude that the assay that we are checking will cross-react with some of those pathogens and will produce false positive results. So in the validation or in the verification report that we should produce at the end of the study for the serological and the nucleic acid detection test, we should provide for the analytical specificity some of this description. Like for serological assay, we should describe the pathogen and the source of the material tested, used in the verification study, number of replicates if we do this, and the results and interpretation. So the results interpretation criteria should be described in this report. And for the nucleic acid detection assays, it's more or less similar, but we should describe the related infectious agent that we test. So the strains, serotypes, all information that we have on this on these samples. Again, number of replicates that we perform during the verification process, and tissues assessed, and the results interpretation criteria. So what we will consider positive and what negative by the end, by the interpretation of the end results. Analytical specificity is more in-depth performed with a larger number of reference samples, as we discussed yesterday in the validation study. In the verification studies, it's very limited, let's say, the need, or maybe because we said from the same reason, difficulties in obtaining such materials. So if it is good during the verification process to include as much as possible of this kind of materials as we explained before, but it will be for very well validated test, it will be of smaller importance, unlike the analytical assessment of the analytical specificity, sensitivity, for example. So what is analytical sensitivity? We already mentioned, and the analytical sensitivity represents the ability of the assay to detect very low levels of a given analyte in a biological specimen. So analytical sensitivity is often referred as a limit of detection. And the limit of detection in the actual is the actual concentration of the analyte in the specimen that can be consistently detected with the assay. And usually we take the confidence level of 95%, so more than 90% of the time the assay will detect this quantity or this concentration of the analyte in the given sample, in the sample at the limit of detection. So how to determine the analytical sensitivity in serological assays? So the analytical sensitivity is determined by endpoint titration of sample with known antibody concentration. So these are and using log2 dilution series. So these samples are usually reference sample, very well characterized sample with known antibody concentration, as I said. So dilution series must extend to at least one dilution past endpoint. So negative will be not detectable. Each dilution in the series should be tested at least in 3, if possible to 5 replicates. And sample used for titration can be spiked sample in the target matrix or standard reference material, as we already said. Just one example in this slide, so that the endpoint titration of the same standard will provide different results or different sensitivity using or tested by different assays. So as you can see here, this is comparison of the ELISA and complement fixation test. And you can see that in different samples, this is for brucella, the sensitivity of the both assays will be quite different in the direction that the ELISA has greater sensitivity than complement fixation test. So for serological assay, what we should include in the verification or in the validation report as well, it is the description of the analyte, whether was the samples that we used were the field or experimental infection samples, the reference samples, the sample type, the matrix, is it a serum or milk sample, tissue, or cerebral fluid, or other type of matrix. So matrices or the diluent use, so the negative sera, the milk, the plasma, the diluent series. Results for each replicates must be described, and the mean, also the mean values, the standard deviation values of the replicates, the coefficient of variation as well. So the criteria, at the end, the criteria for endpoint determination, like the last dilution in which all replicates will give a positive results, it's also have to be included in the verification report. Now we will discuss or just describe how we will assess the analytical sensitivity in the nucleic acid detection assays, or more precisely, we will discuss on the real-time PCR assays as we mentioned, as quantitative assay. So the analytical sensitivity can be estimated using so-called dilution to extinction experiments, in which we perform a serial dilution of a known quantified amount of targeted analyte in appropriate sample matrix. So this known quantified amount might be from an in-house or national or international reference standard, or a field sample whose analyte concentration has been previously determined. So the dilution series must extend the same as we said for the serological assays, the same is for the PCR. So the dilution series must extend at least to one dilution past the endpoint. So we have to have dilution in which we will have all samples tested negative. So just to describe this, giving a practical example. So for example, if we have a quantified sample material containing 10 to 8 copies of, for example, lumpy skin disease virus, and we spiked into 10 microliters of serum, and we want, and by doing this, we will achieve a concentration of 10 to 7 copies in microliter. Then from this sample, from 10 to 7 copies sample, we perform 10-fold dilution series until we reach the quantity of 10 to 1 copies on a microliter. So this experiment, as we previously said on a couple of occasions, should be repeated at least 3 times. So it should be done in triplicates. So by the end, when we test the samples of this in this dilution series, all replicates by the assay, by the real-time PCR. So if all replicates at, for example, at 10 to 3 copies in microliters were detected, but no sample in the dilution step where we will expect the concentration of 10 to 2 copies is detected, then the limit of detection could be conservatively estimated as to be 10 to 3 copies in microliter. So if we would like more precise estimation of the limit of detection, it is needed to perform a second stage experiment in which we will determine the limit of detection with a greater certainty. So this series of dilution will require to perform two-fold dilution of the samples, one of the sample before the last detected in the 10-fold dilution series, and this will encompass the interval between 100% detection and 0% detection performed with the previous experiment when we performed a 10-fold dilution series and detection of the analyte. So we said previously that the limit of detection is often chosen to be 95%. And what practically this means? It means that if in an experiment we use 100 replicates of reference positive samples, this will correspond that to the dilution where 95 replicates for the analyte will give a positive result. Or if the experiment is performed with 20 replicates, this will correspond to the dilution where the 19 of the replicates for the analyte will give a positive result. Or if we use 10 replicates, this will correspond to the dilution where all 10 replicates of the analyte should be or must be positive. Theoretically, it will be 9.5, but we will expect, or we should expect, or we will calculate the limit of detection point, the dilution series or step in which all 10 replicates will give us a positive result. And we can say that this point on the scale, or this quantity, if we have standard with quantified material, will be our limit of detection of the assay with 95% of confidence. On this slide, there are calibration curve parameters which are described, which are used to evaluate the performance of nucleic acid detection test, actually the real-time PCR. So, as we said, the limit of detection is the last dilution with all replicates classified as positive. So, in the introduction of the standard curve of all calibration curve parameters, we use the terms as slope, the R2 value or linearity, and the PCR efficiency. All of these parameters usually are given and calculated by the software of the real-time PCR machine, as you can see on this slide here on the right side, where you can find the values for the R2, for the slope, and for the efficiency of the PCR. And this is another example of another standard curve in which you see here the linear presentation of the amplification plot, the log visualization of the same amplification plot in this serial dilution, and this is the achieved linearity and with provided parameters for the slope, for the R2, and for the efficiency of the PCR in a different PCR machine. This might have different interface, but more or less all the machines will provide you with this calculation. Now, just let's try to explain some of these terms. For example, for the PCR assay, the lowest concentration of the analyte that can be detected with a stated probability can be determined by plotting the data from the positive replicate results versus the analyte concentration and expressed in the CT values or number of copies. So in this example here, you see if we start with the 50 nanograms per microliter of concentration in the strongest or highest positive sample, or the most concentrated sample, and then we perform 10-fold dilution, of course, the concentration will fall down to 5, 0.05, 0.05, and 0.005 nanogram in microliter. That's plotting on the plot will give us the different CT values for different concentration. For example, if we start, if the sample with 50 nanogram per microliter will give us a CT value of 15, then if this will be the perfect experiment and we will have the slope of minus 3.3, then the sample, the third sample with a concentration of 0.5 nanogram in microliter should give us a CT value around 21.6. This is in theory or in ideal situation. So the PCR efficacy, but this will depend on the PCR efficacy and the efficiency of the PCR can have significant impact on the robustness and the precision of the assay. So the efficacy of the reaction is determined by a number of factors, including primer design, cycling conditions, and the reagents used for the reaction mixture. So the PCR amplification efficiency is typically established using this calibration curve or standard curve analysis, and it makes sense to use the dilution series for performing the limit of detection. And in these studies, we will have to use, or we should use, a strong positive samples, which will give us at least 5 to 6 of the dilution series or quantification of primer dimers. So in the picture, in the lower picture, you can see that the difference between the CT values from the most concentrated to the next one, it's pretty close. And then we have more or less equal distances. And then at the end, again, we have very close CT values for the last samples in the dilution series. So this could mean, as we said, that probably during the pipetting something was wrong from taking the sample from the most concentrated to the next dilution step, and from that point on, if everything was okay, then we will have a correct let's say distances of between the each dilution step. Or this might be a reason because we in the start in the original sample we have some inhibitors of the PCR reaction which will be diluted as in the dilution step. So when the level of the inhibitors will be lowered to the extent that it will not affect the PCR efficacy anymore, we will then gain or we will achieve good PCR efficacy. So this is some of the explanation why we could sometimes obtain efficacy of the PCR higher than 100%. Other than that, of course, we all know that it's not possible that from one copy to the next step to get 3 or more replicates. So we talk about the PCR efficacy. Other parameter that we mentioned is the linear dynamic range of the reported range, or R2. And just briefly, we will not go too much into details, but just to explain that the linearity of the range can be established by the calibration curve, so standard curve analysis, where the R2 value, or the coefficient of determination, of 1 indicates a perfect fit to the data points. So generally in the real-time PCR assays, the R2 shouldn't be, the value of R2 shouldn't be less than 0.99. And the linearity and reportable range should be carried out on at least 5 log dilution, as we said, on the targeted nucleic acid extract from the appropriate sample type. Of course, performed in triplicate. As I mentioned previously, you don't have to bother with this because in the real-time PCR machine, your software will automatically calculate the value of R2. Just during your verification of your assay, you should include this information of your experiment and evaluate whether or not your assay performance is as required by this value. So in your when preparing or evaluating the standard curve, the R2 value shouldn't be lower than 0.99. So at the end, just to summarize what parameters or what we should describe when we will perform the verification, prepare the verification report for the molecular nucleic acid detection test assays. So we should describe the analyte used, so the virus or the plasmid sequence or the field sample if it's in question. So matrices and diluent uses, so buffers, negative DNA, negative tissue extracts, etc. Concentrations. This is optional if we have in our possession reference material with quantified values that we know the quantification. So, for example, nanograms in microliters or genome equivalence, number of copies in microliter or TCID, etc. And etc. And the methods quantification used to determine these values. So different spectrophotometers like nanodrop or qubit or tissue culture, etc. Dilution series also and expected concentration based on the starting of the highest concentration. CT values for each replicates, and we should describe or express the mean values, the CT, of the CT and the standard deviation of the replicates and or the coefficient of variation. Criteria for the endpoint determination. For example, the last dilution with all replicates positive. It will represent our limit of detection, and everything above this will be considered negative. We will see this more in the next coming days when we will include to this. Now we just focus on the analytical sensitivity. We will discuss tomorrow for the repeatability and reproducibility, and on Thursday about measurement of uncertainty. When we finish this, all these parameters should be included, and it will give us our final key, let's say, how we will express our results, how we will actually interpret the result, the final results. And of course, as we said, as I previously said, in the verification report, we should include the values for the standard curve with the slope, R2 values, and the PCR efficacy value. So with this, I'm concluding this presentation for the analytical specificity and analytical sensitivity of diagnostic of serological and nucleic acid detection assays. Thank you for your attention, and we are now open for your question. Thank you.
Igor, thank you very much for a very interesting and clear presentation. I think for now we will have a coffee break, let's say for 20 minutes. So we start at 9:25 or 9:35. And then please make ready your questions for our experts, and see you soon. Can you hear me? Can you see me? Please put something in the chat.
Can hear you, but we cannot see you.
I think we can.
Okay, it's good.
See you, yes.
Okay, Ivanshu had a comment, maybe if he's ready. Okay.
Yes, just hello again. Just to compliment on the presentations of Vladimir and Igor, I think it's very important to understand the slope, and just I would like to complement with a few explanations to contribute to these presentations with the theory and practice of the real-time PCR. So I'll share the screen with few slides, just as I said, just to complement with a few information. You see, understanding the slope is extremely important. First, because of the theory behind the reaction, what is happening in the PCR reaction? We have doubling of the number of DNA target molecules in each next cycle. So in cycle 1, we have X number. In the cycle 2, we will have too much that number. In theory, yeah? Of course, there are sources of errors. So the sources of errors will be the heating of the thermocycler, the stability of the master mix, the concentration of individual components, the measurement of fluorescence. So there are many sources of errors, but we don't see them. What we see at the end of the reaction is the increase in the fluorescence, which should be in very, very high correlation with what is happening in the theory of amplification. So we should see doubling of the fluorescence when we have doubling of the molecules in the PCR reaction. So this is the kind of theory of the development of the slope or calculation of the slope. So the correct correlation of the slope is important. Why? Because of semi-quantification or quantification. I'll explain why do we call it semi-quantification and why do we call it quantification, yeah? So if we have 4 samples, this is really very, very much a theory, what you see in the table. It's not reality, it's just the theory of the PCR reaction. We have 5 samples with different numbers of DNA. So in the first one, we have 1 DNA molecule, in the second one, 10, 100,000, and 1 million, and so on, yeah? So when we amplify, they will all amplify under the same rules. All will double the amount in each consecutive cycle. But when will they reach the cutoff point is different because of the different startup molecules after the amplification. And this is what we see here on the graph. So the sample that has the most number of DNA copies will have the lowest CT values, and the ones with less and less will have a later and later CT values. So they will come positive much, much later compared to the first one. But it is important that during this amplification, the consistency of the slope is followed. So therefore, with these 10-fold dilutions, we have to determine the slope and understand that it is within the acceptable limits. Now, just to prevent confusions, you know, the slope depends on the dilution. So in the practical interpretation of the slope, if we have 10-fold dilution, can you see my Excel file here? Is my Excel file visible?
Yes, we can see. Yes, it's okay.
Okay, perfect. So if we have 10-fold dilution, so if we do this in highlighted in green here, so the practical explanation of the slope is how many cycles do I need to amplify the number of molecules 10 times? And the answer here is 3.32 as our colleagues already presented. But if we do 50-fold dilutions or we do 100-fold dilutions, then the slope will of course change, because the question will be, in that scenario, how many times do I need, how many cycles do I need to amplify the number of molecules 50 times? So it will be a slope of 5.64, or if we want 100-fold dilutions, 6.64. And in Excel, for everyone, if you do not use the machine, you have this built-in function in orange, where you can calculate the slope manually based on the dilution. So it's log of the dilution factor with a root of 2, because twofold amplification is after each cycle. The other very important issue is that the calculation of the slope and consideration of the slope is valid only in the linear part of the amplification curve. Because you see on the left slide here, we have the theoretical amplification, which will be endless. If we calculate every cycle, we will have double number of molecules and it will be endless amplification. But it is not happening in the practice. In the practice, we have this linear part here and we have the so-called plateau phase, which appears because all the DNA copies are spent, all the materials, source materials of the master mix are spent, all the probes are spent, so we do not have a substrate to amplify anymore. So therefore, the value of the slope is valid only for the linear part of the amplification curve, not on the plateau phase. That's also very, very important to quantify for quantification. The importance of the slope is in the context of what I mentioned, semi-quantification or quantification. The semi-quantification applies when we have two samples with unknown amount or number of DNA molecules as a startup molecules, and we compare the samples between each other. If we have appropriate slope, we will be able to calculate very precisely what is the ratio between sample 1 and sample 2. So we can say, okay, sample 2 has 10,000 times more DNA molecules or more pathogens per unit of volume, per microliter, 10 microliter, 100 microliter, whatever, compared to sample 1. But we cannot say the absolute amount of the startup DNA in the samples. We can only compare two samples. So this is semi-quantification. Some laboratories are offering also quantified DNAs or RNAs, so or consortia whatsoever. So if you search on the European Virus Archive on internet, you need to create an account in order to have access. For many diseases, you have quantified DNAs or RNAs. So you can purchase a sample with 50,000 or 500,000 or 5 million DNA or RNA molecules per microliter. So in that scenario, you have precise number of DNA or RNA molecules. And when you dilute the sample, you can clearly know which amount of DNAs generates which CT value. Of course, if the slope is appropriate within the acceptable range, that will reflect the quantification, or this will enable us to quantify the number of DNA or RNA molecules in our samples. So we can run one quantified, commercially available sample with known amounts of target DNAs, and then compare the others against the quantified amount. In that case, we can say, okay, in sample number 1, with CT value of 12, I have 500,000 DNAs per microliter, and in sample number 2, with CT value of 34, 35, I have 500 or 700 molecules of DNA. So this is this difference between semi-quantification and quantification. In real-time PCR, the analytical sensitivity, if we quantify the number of molecules, appears to be enormously high. So enormous means that the PCR will probably detect within tens or 5 or less than 10 or a few tens of molecules. And this raises another epidemiological question, which is, can 5 molecules of pathogen XYZ induce a disease in healthy animal? Which is the infectious dose of certain pathogen that should be considered as positive, as epidemiologically important quantity that can cause transmission of the disease from one animal to the other. So these are the very, very important aspects that we should consider during the determination of the slope and the quantification or semi-quantification of the PCR assay. Thank you very much for this.
Thank you, Ivancho. And now let's go back to our questions. And I will read them, and then our experts will give answers. I think for the first question from Ethiopia, we already clear. We had these replies during the presentation. But then the question from Greece, in the case of quantitative ELISA test using a commercial kit, do I need to measure absorbance values and calculate mean value SD, and so and coefficient of variation also results are expressed as positive or negative? This is the first question to our experts. Might someone take it?
Okay, maybe I'll try to give the answer. This will be clear on Thursday when we will talk about measurement uncertainty. So the cutoff value presented by the kit producer may not be the same cutoff value that will be valid in your laboratory. Therefore, during validation, you have to do measurement of optical density, and you have to do normalization of your ELISA result, and then to calculate what is standard deviation. And from standard deviation, you can of let's say 10 repetitions of the same sample, then you will know what is standard deviation, and then you can translate it to the cutoff value. So maybe the cutoff value will be different in your laboratory, slightly, but it will be different. But we will talk more about this when we will talk about measurement uncertainty.
Okay, thank you. The next question is. Okay.
Sorry.
Yeah.
Again, I'm sorry. I don't want to interrupt you guys. Just to prevent misunderstandings in this question, the colleague asked if we can interpret. I understood the results directly. In any ELISA test, we have what Vladimir mentioned, the normalization. So we have to calculate not only the optical density, but if it is indirect ELISA, we need to calculate the percentage of positivity compared to the internal positive control of the test. So this is this kind of normalization to calculate background values and so on. There is in each instruction package there is the formula how to calculate the percentage, or in competitive or blocking ELISA, we calculate percentage of displacement and percentage of residual binding. So these are extremely important normalization procedures to give you the value that should present your cutoff. So you must be aware that these cutoff values and these calculations, this normalization, what Vladimir mentioned, is extremely important to check if the assay performs properly and if the values of this assay should be considered for interpretation. And of course, in the ELISA, we always have this semi-quantitative component at the beginning. We need to measure optical density. We need to convert percentage of positivity, percentage of inhibition, residual binding, or whatsoever, and then give the qualitative interpretation. Yes, this is positive. No.
Hello, Ivancho, are you with us? Well, Ivancho is freezed. Okay, maybe we proceed with questions. Can you hear me, by the way?
Yeah, just to maybe Ivancho mentioned before freeze. This I wanted to add to the comment that because the colleague asked, even though the ELISA, if he used the qualitative ELISA, do they need to calculate the standard deviation and variation, and this is the point that all ELISA actually with what Vladimir presented yesterday actually will give us quantitative results, which will then should translate to qualitative interpretation. So in general, you have quantitative data, either optical densities or percent of inhibition or percent of positivity. Still you have quantitative data behind it.
Okay. Ivancho, do you want something to add something, or you're completed?
No, thank you. Thank you. My Teams restarted by itself, so I don't know. So I just wanted to explain the importance of the interpretation of data in the ELISA, whichever concept of ELISA is, indirect, competitive, blocking, whatsoever. Yeah?
Okay, thank you very much. For the next question, well, from Alpha Team, when we perform the interlaboratory assay, is it important to have the same PCR efficiency? Is it also necessary to have some brands of instruments real-time PCR machine performance are not allowed the same? Okay. So who will take this question?
Okay, I was talking about different machines. So if we think interlaboratory testing as a proficiency testing, no, you just have to correctly identify the samples you have received, and you don't have to work on the same PCR machine. If you think about verification of the method, also not necessarily you have to have the same PCR machine. It will be good if you have the same PCR machine. It will make your life easier. But if you have different machines, you have to consider what are the differences and how to make these differences not influence significantly on your results. I don't know if I gave the answer.
Well, I think it's clear, but okay, Ivancho.
I think it's very clear. Just to complement in another dimension, because the colleague asked ring trials and proficiency tests. In the ring trials, the provider of the ring trial will not ask you about analytical sensitivity, about slope whatsoever. These are the actions that you should optimize before you start the testing process. So the provider of the ring trial will ask you only what is the CT value of this sample, or the status of this sample. Is this sample positive or negative, or eventually weak positive or weak negative, So the ring trial is targeting laboratories with established internal verification procedures. So they assume that you have done everything before you applied for the ring trial. That's also very, very important. That's why this verification procedure is extremely important to generate appropriate results. Thank you.
Thank you, Ivancho. Thank you. So the next question is from Hafsa Madini. What is the acceptable limit for CV, which is, I believe, coefficient variation? Who will take this?
Yeah, I can try.
Okay.
This will be also explained during the next days. But in general, acceptable level of coefficient of variation for the molecular assays is below 5%, and for the serology assays, it's between 10 to 15% coefficient of variation. Usually, these are the range in which are the acceptable level of variation for these two types of assays.
Okay, thank you, Igor. Next question is from Morocco. What do you mean by endpoint determination? Please, experts.
Yeah, the endpoint determination is actually when you use replicates of a sample in a dilution series. Then this is the last dilution in which you find all sample giving the positive result, or you detect the analyte of interest. So this is the endpoint determination.
Okay, thank you. Now it's clear. The next question is the processing of samples by grinding affect the analytical sensitivity in real-time PCR? So does it affect analytical sensitivity?
Okay, I switched my microphone first. No, grinding should not affect the sensitivity. On contrary, you need to have a well homogenized sample if you want to have the maximum yield of your RNA or DNA. But for analytical sensitivity, I don't know why you have to grind your sample. Only in testing of field samples.
Okay, the next question is from Hakan Tabak from Turkey. Does international amplification control must be used in the verification process? So can someone take this question?
Yes, we said in the verification process, you should use a reference sample panel, well defined, and usually, as we explained, it should include samples with the different concentration level of the target in the operating range of the assay. So low positive, high positive, and medium positive samples. The internal control is usually, now if we are talking about PCRs, molecular assays, internal control are used in the assay just to control each step of the process, including, of course, the extraction and the possible effect of the inhibitors. But when you do validation, verification, actually, it will also depend on the reagent that you use. For example, in case you have an internal control of some housekeeping gene, for example, or some synthetic DNA, then you already have a duplex PCR at least. So you want to amplify your target sequence, and then you should amplify the internal control sequence. So some kits, some amplification kits have a limitation when it comes to multiplexing. So this is one consideration. So if you have appropriate kits for multiplexing, this shouldn't be a problem, and it should be included. But in case the kit is not designed for multiplexing, it might be an issue. I'm not sure if all agree with me. I would ask my colleague Vladimir what he thinks about this question.
The categorical answer, should I use in verification internal amplification control? I would say is it absolutely necessary? Not. It is advisable, of course, particularly when you test field samples where you can have inhibitors in your sample. But it is not absolutely necessary to include in your verification process. But if you will include, then it is welcome.
Yes, I would just add. So if you use the reference sample, which are usually inhibitor free, let's so to say, so not as Vladimir mentioned, the field samples, you wouldn't expect, or you shouldn't expect, let's say, any interference from the matrix from that point of view. But of course, if you use field samples, it will be it should be let's say advisable, or first to assess the eventual presence of inhibitors, and then to continue with the verification process.
Thank you, experts. The next question regarding the regression curve, how to calculate it if we have experienced 10 different runs, for example, with different standard curves, and how to calculate or validate sample results to the regression curve. Please. So who will take this question?
So I'm not really sure I understood the question exactly.
Well, let me read it again, but it's from.
I'm also Artem. I think the question refers to dilution curve instead of regression curve, or something else.
Well, maybe, but I just read from what was asked. Maybe we would suggest Yumna. Unfortunately, I don't see. Unfortunately, I don't see the country. Yes, please.
I'll try to give an answer. So if the question is about the dilution curves, standard curves in 10 different experiments, let's say, then the evaluation of the results will not, let's say, again, the evaluation of the results will be on the results or the values of the efficiency and the linearity and the slope for each experiment. So in each of these standard curve experiment or dilution series, you should get values for these parameters within the let's say desirable one.
Okay, so
and I think Igor, you had one slide in your presentation presenting the CT value and the concentration with the correlation curve. So maybe that slide can help our participant to clarify. So that there was a correlation slide between the CT value and the concentration. So once the slope is within the acceptable values, then you can quantify the assay by correlating the CT value and the concentration in the sample.
Okay, thank you. But if we are not clear, we will ask this participant to rewrite this question more clear. But the next question is regarding, so they suggest that we also need an example for LOD, which is limit of detection by use of conventional PCR. So maybe
yes.
Comment this.
Vladimir, would you or should I?
I think it's not very complex answer. So you continue, please.
Okay, so yeah, as we said, usually we use limit of detection for the quantitative method. Real-time conventional PCR is considered to be qualitative assay. So, but I think that's the one way to do it would be in comparison to, for example, if you have a conventional PCR for certain pathogen for which you have also a real-time PCR, then by producing standard curve analysis, and probably, or if you can quantify this with real-time PCR, and you determine the limit of detection, then you use the same panel, the same dilution series with the same samples running the conventional PCR, and then you can compare, let's say, just provisionally, to which CT value you will obtain a positive result in your gel. So in this way, somehow you can try to estimate the limit of detection of your conventional PCR. In practical use, let's say, we usually laboratories will usually use the real-time PCR assay as a screening methods because of their high sensitivity. Unlike the conventional PCR, which usually have lower sensitivity than in comparison to real-time PCR. So in case of in the diagnostic aspect, you can use conventional PCRs as a confirmatory methods, for example, to confirm the results, the positive results gained in the real-time PCR. But once you, let's say, determine this limit of detection, and for example, if you get a positive result on a real-time PCR, which is, for example, 35 CT, and you establish that you can obtain a visible band on your gel by conventional PCR method up until 32 or 33 CT value, then it is of no use. So in this way, somehow you can, let's say, in connection, determine the limit of detection of the conventional PCR. Other than that, it is not a thing that you can use because, as I said, conventional PCR is considered to be a qualitative assay.
Okay, thank you, Igor. If other comment, then I will go to the next question from Vietnam. If the lab use the commercial ELISA kit that validated by a kit producer with CA attached, the lab has to do validation again or just do verification? I think we had this yesterday, but please comment again.
Well, if I understood the question correctly, only verification should be conducted in that case.
Yes, sure. So the next, let me go to the next question again from Vietnam. How to calculate limit of detection for ELISA test based on positive control supplied with the kit? Please, someone.
Well, no, you cannot calculate limit of detection with the positive control. The positive control in the kit is just for normalization of the results. So you need some extra serum with known titer, either by other ELISA or serum naturalization or any other test, and then you can make limit of detection, but you cannot do it with the positive sample within your ELISA kit, which is already pre-diluted before packaging into the kit.
I would like just to complement to Vlado's answer on this. There are some, usually this is when we talk about diagnostic assay ELISAs for diagnostic of infectious diseases. But there are some ELISA kits for, let's say, detection of the level of some hormones or some other analytes, which comes with a standard, which will quantify, because in those assays are used or developed for quantification of the of these substances. So by titration of this standard inside, you can let's say determine the limit of detection of that ELISA, and just in this case. But no, this cannot. An answer it's correct. It cannot be done by the internal positive and negative control in the kit.
Okay, thank you. Our colleague from Morocco wanted us to comment about endpoint determination. What is this? Maybe repeat. I think we had already.
Yes, we explained already.
We already explained. Okay. Is the processing of samples, well, we had this all. I think this is just repetition, repeated. Yes. When we consider the sample is negative with which CT, so they ask about CT value cutoff, I think more than 35 or 40, and why? Maybe comment?
Yeah, I would not go into explanation about this because the next days we will provide the answer of this and what you should do and perform in your laboratory in order to reach this conclusion.
Maybe if I can just add something. There is no universal rule for real-time PCR or which CT is positive and which CT is negative. It depends on the validation testing. So the designer of the kit should let you know that a cutoff for positive negative is 35, sometimes it's 38. It depends on the design and performances of the kit. So it depends from an assay to an assay.
Okay, thank you. I think it's clear. We have two more questions. First one is, prior to performing PCR, do we still need to perform DNA, RNA quantification for each dilution?
No, it's not necessary to do that. If you have a quantified sample and you know the amount in the starting material, then by using this calculation, as we already presented, you can estimate or calculate the quantity in each of the diluted in the dilution step.
And from the same participant, the question is also in setting threshold. Do you recommend auto or manual setting?
Yeah, I think that usually the threshold is automatically set correctly, but the general rule, let's say, would be if you would like to do it manually, and maybe it's more implicative when you use maybe for the standard curve, let's say, analysis. And then the general rule is that the threshold should be set in the first third of the linear in the exponential phase. So we should provide some maybe example of this in the next day, just to be visually clear. But other than that, automatic threshold will do the job in more than 90% of the time.
Thank you, Igor. Then one question from Sierra Leone. Should the triplicate samples be analyzed in the same run or different runs for analytical sensitivity?
Sorry, I didn't get the question. Can you just repeat once again?
Yes, prior to performing PCR, do we still need to perform? Should the triplicate samples be analyzed in the same run or different runs for analytical sensitivity?
Yes, always in the same run. That's why it's we call it triplicate. So in the same run, you do triplicates of each sample in the panel, whether this is the repeatability panel samples or the dilution series in the standard curve. You always perform each sample you test in triplicates in the same run.
Okay, thank you. Other reference samples of sera from animals infected by all species strains that the test should detect. Again from Sierra Leone. So reference samples of sera from all animals infected by all species strains that the test should detect. Well, question is not very clear, but maybe comment something.
I think the colleague is asking if we should have a reference sera for each species that we test. Or if we need verification for each species. If we test cattle with the same assay, we test sheep, we test goat, we test pigs or whatsoever.
Well, then our reply is yes. To verify, we need all of them, right?
Yes, the verification for each species, yeah.
Yeah. Okay, then the next question is from Morocco. During the evaluation of immunochromatographic test, how can we calculate the endpoint stability accurately? May someone reply this for immunochromatography? Well,
I can reply it. Immunochromatography usually refers to the small field applicable rapid tests for diseases. So the whole verification is expected to be done by the producer and supplier. Actually, the producer. So the developer of the test in the immunochromatographic test is investing in laboratory investigations that the test work properly. So what the user needs to do only to put the droplet and wait for the results XYZ minutes as recommended by the producer. So immunochromatographic tests have built-in controls and the validation is performed at the level of the producer. So the end user should do nothing, just put a droplet. Thank you.
Okay, thank you very much for
maybe if I can add, yes, the end user does not need to test limit of detection, but in my yesterday presentation, Ivanchuk has shown a slide with it a few minutes ago. What we were doing when the test was developed, during the developing here in Zagreb in Croatia, so we were simply testing different concentration of the virus applying to the test to see what is detection limit in means of virus titer. But this was just during the development and validation of the test, and you don't need to do it in your laboratory.
Thank you, Vladimir. Next question from Cameroon. Will you advise to use expired PCR reagents after verification if reagents are well stored? Someone please reply. So
well, yeah, this is the interesting question, and of course, there is a procedure for verification. In case you have any differences from the originally, let's say, valid and verified method. So of course, if you perform verification with the same panel of samples that you use when the kits are not expired, and you will obtain the same results in comparison with the reference material, then you can, because it's up to the laboratory management to provide a proof that the reagents in question are still performing according to the prescribed, let's say, standards. So my answer would be yes, but it should be a procedure and it should be very well documented. And of course, at the end, the head of the laboratory will be responsible for the results that are issued by the laboratory. So it must be sure that the results they are producing are valid. So it's a more of the need of the laboratory in case they would like to use such kind of reagents.
Thank you, Igor. The question from Nada Osman from Sudan. For the significance of results in Sudan, I found brucellosis in human in titer 320 and without symptoms. It could be considered negative. I think is the question, could it be considered negative? So
yes, this is more let's say now question of the diagnostic interpretation of the results. and whether this titer would mean infection or maybe a background if the person, let's say, has recovered from brucellosis, or maybe it's in the beginning phase. But I'm not an expert in this, but in my let's say knowledge, I think that this would need to undertake another test in maybe 10 days or so or less, and to see if the disease titer increase or decrease to evaluate whether or not in which phase actually this person is.
Okay,
so, but it's very specific to this disease and to the clinician interpretation and use of this data. So there must be recommendation how to interpret such titers. But in generally speaking, I think this would be approach.
Okay, thank you. Next question. Some commercial ELISA kit can detect antibodies against natural infection, but not the antibodies against experimental infection. Would you please kindly tell me the reason? Okay, this is from Ethiopia.
Yes, I think we already discussed about this, and we said it even yesterday. So each kit, when we develop the kit and when we start the validation, and accordingly, as we are now talk about verification, must have stated the purpose of use. So we must clearly know why this test is designed for. Is it designed to detect let's say a natural infection, or can detect the pathogen regardless of the status? I mean, is it the vaccinal strain or the natural infection? And then you have the test. We talked about this today. It would be the exclusivity of the test. The test developed to detect some part of the modified organism, usually used for the vaccine, to detect this part, which is different from the original or the wild strain of the pathogen in question. And this is why some ELISA, of course, can detect natural and cannot detect vaccinal or other way around. So they are developed and optimized in such way to detect the specific pathogen of interest. And depending on why we are using the ELISA, either we want to screen or we want to imply DIVA strategy, or to differentiate the vaccinated from infected animals in case we have some disease which we want to eradicate, but we also apply vaccination, and then after some time we would like to assess the status, and we want to be able to differentiate between those two. But there are some diseases for which it's not possible to make such kind of tests.
Thank you, Igor. Next question is from Kamilika. In real-time PCR, how to interpret the results using positive control and internal control? Does this internal control use a positive control? So with this question, we go back to principles of PCR, but may someone reply?
So if I can, can I use the positive control in the PCR real time only without the internal control, and can consider the result positive as positive? This was the question.
Igor, it was the previous question from Kamalika.
Yes.
How to interpret the results using positive control and internal control. Does this internal control use as a positive control?
Okay. So, briefly, I think it will be also a topic touched in the next days, but just there are different type of quality controls that we are using. One of these is the positive control that we use, and it's the usually and can be the control of the amplification process, and also can be internal control, which is usually used for the control of the whole process from the extraction and also the amplification process. So the intended purpose or the value or for both controls is different. So with the positive control, we would like to assess the amplification process, whether or not we have some let's say problem during the amplification phase. Maybe we forgot to include some component, or maybe there are some other, let's say, problem, maybe technical problem. And with the internal control, we would like to see if from the starting point, if we have successful extraction of the material, and then to assess the influence of possible inhibitors in the sample originated from the clinical sample, for example. So usually when we perform a PCR diagnostic, it is advisable to use internal controls in order to be sure that your negative result of the tested sample, it's really negative and it's not a result of some inhibition or maybe poor performance of the extraction during the extraction process, because the amplification positive control will be positive because your master mix is okay, you perform everything well there at that stage, but you had some problem in the beginning. So this is why the internal control it's important to be included. And if the internal control result is negative, then the assay would be considered as not valid, and you should repeat the whole procedure again. I hope I understand and I replied to the question correctly.
Yeah, it was quite clear. Next question from Sonia from Tunisia. Can I use the positive control in PCR real time only without the internal control, and can consider the result positive as positive? Thank you. So can we do without internal control if it's in the kit?
Okay, I'll try to give you the answer. So if you talk about internal amplification control, if it's included in the kit and you didn't put it, and you're positive, and your sample is positive, then the sample should be considered positive. Although you have to take care, was it a cross-contamination, but it's a different story. But internal amplification control is used for negative results. So for every negative result, your internal amplification control should be positive. Then you know the sample is really negative. So if if the sample is positive, then you basically do not need internal amplification to be positive.
Okay, we have the next question. Should we repeat the validation procedure for an in-house method if one or more reagents are replaced for analogs ones? So if you change the reagents only and you have performed the in-house validation.
Yeah,
I think that only verification is needed.
Yes. Yes, I would refer that to the previous reply. The same thing is in this case you should do the comparability study to see if the reagent that is replacing the original one perform as the previous one. So comparing, but this, yeah, it's always good to have this planned in advance. So before you run out of the reagents, of the original reagent, and you purchase someone which will replace that, you should run in parallel the test, and in this way you compare the performances of both, or the influence of this reagent in the whole assay and the outcome result of the assay. And if the comparison is if the results are comparable, then you can just perform this limited verification and you continue as previously.
Thank you, Igor. Thank you. And we have a set of 5 questions again. One from Morocco. For RT-PCR, we should determine limit of detection method, or both limit of detection of PCR and limit of detection of method. Please comment. Is the question clear?
I'm not sure I understand.
Well,
I don't know about the others.
I will try to read it again.
No, I read the question, but I don't actually understand limit detection of PCR.
I think limit of detection should be determined for each individual method. So if you run a real-time PCR, you do a real-time PCR limit of detection. If you run conventional PCR, you run conventional PCR limit of detection. So each method should have its own limit of detection determination in order to understand the assays.
Thank you, Ivancha. Next question is from Dr. Ali Raza, Pakistan. Commercially prepared ELISA kits, even after expiry date, gives valid results for controls. Can we use this kit for screening of samples? If yes, then is there any paper or proof that allow to issue results for sampling? Please comment. It's a sensitive question again for expired.
I think that the same applies as for the real-time PCR. So if it expired and if you have procedure how to convince different bodies that the result is still valid, and you have recorded everything, then you can use it by the approval of quality manager.
Can I just add something about that? For example, if you are you have accredited laboratory and you do ELISA testing with expired kit, and you record the batch of that kit and put it in the report, if something goes wrong and that goes to court, then you have a big problem, because you have issued the result with the kit that is expired. So I would not encourage people to use expired kit for official testings.
Thank you very much, Dan. This is a very valuable comment for this sensitive issue, because it's actually not good to use any expired stuff. Again, question from Nada Osman from Sudan. The point of selectivity was not clear for me. Okay, maybe clarify again what is point of selectivity.
Yes, the selectivity of the assay actually, as I said, is to the ability of the assay to detect the target for which is designed and differentiate between all other impurities, other organism, or some buffer, let's say, components during the run in the same in the assay run. So unlike the inclusivity and exclusivity, which are more concerned about the ability of the assay to detect, let's say, the pathogen on a species level, so more broader, or exclusivity if we want to just the assay to detect a specific, let's say, variant, specific type or strain or genotype of some pathogen. So it is the ability of the assay to distinguish, to include or exclude the target pathogen or to divide them generally or more specifically. And selectivity is the ability to detect the target in the presence of some other, let's say, inhibitors, as I said, or other interference. So ability of the test to select the right target in presence of other interfering factors.
Thank you, Igor, for this very clear reply. The next question is, in antibody ELISA test, the structural differences between antigen that is coated on ELISA plate to the antigen of wild target virus could have an impact on diagnostic specificity and sensitivity. Someone please comment if the question is clear.
I think that the question is clear. Depends what is the magnitude, what is the extent of the difference, and where is the difference? Is it related to the epitope for antibodies or not? So this is rather a question of specificity of the test. So if there are big differences, then yes, you can have lower sensitivity. But if these differences are not related to antibody binding, then you should have a valid result. So it's difficult to say yes or no. It is relative to the changes, to the differences of the wild type antigen and the antigen used in your ELISA coating.
Thank you. The next question is from Sierra Leone. How do I interpret analysis of the same sample when conventional PCR is positive but real-time PCR is negative? Well, it depends, of course, on the disease, but please comment. For example, for rabies, if one test is positive then and others are negative, the result is positive, accepted as positive always. But maybe if, our experts could add something.
Well, I'm not an expert in rabies, but I'll say in general, given that both tests are done properly and they are not false negative, it could be question of mutation of the virus in gene location for probes for the probe and primers for real-time PCR, because primers and probe for real-time PCR, they bind on one part of the genome and for conventional PCR on the other. So maybe there are mismatches in your real-time PCR primers and probes, and that's why you got a negative result, given that it is not some mistake in your test.
Can I add something on this point?
Yes.
The only thing you can do to be sure which result is valid is to sequence your PCR product of conventional PCR, and then you will see if the sequences are from that virus you were targeting or not. So maybe it's not non-specific reaction, then real time will be correct, and if it's specific part of genome, then actually it's positive result, and the real-time PCR did not detect it from reasons that Vlado just told.
I would also like to add just that first, before you go into all this, you should first validate both results. First, to validate is the result actually in the real-time PCR really negative, and is the is the conventional PCR really positive, or maybe it's some contamination in question. So if you validate first that you have really positive result on the conventional, and your negative result in the qPCR is not a result of any mistake during the process or inhibition or whatever, or as Vlado said, changing in the primer binding sites, then you can move forward, let's say, and to explore other possibilities. But first validate both results.
Yes, and
Ivan,
sorry, one more addition. A few questions before this one. There was another question when the real time is positive and the conventional is negative. I think the topic of this course is exactly to prepare the diagnosticians on these questions. So number one, analytical sensitivity of both real-time and conventional PCR should be clarified before you start testing. So a good diagnostician will always know which assay is analytically more sensitive and which one is less sensitive. In this case, in a vast majority of the cases, if not always, the real-time PCR will be more analytically sensitive compared to the conventional PCR. So therefore, if the real-time is positive and the conventional is negative, and I know that in my assay, this is the analytical sensitivity, I would always consider this result as positive, only because I know that the real-time PCR analytical sensitivity is much higher or XYZ times higher than the conventional PCR. The other question is, I think Dejan gave a very good suggestion. If you understand your assays, you know very well the performance of your real-time and your conventional, and it works regularly on daily basis, you know that both of them are optimized, so then there is something wrong, most probably with the master mix or the sample. But if the repeated sample is again the same, conventional positive, real-time negative, send for sequencing, clarify the sequence, check if the area where the probe matches is changed, is mutated, and then go for another kind of phylogenetic analysis. By the way, I think most of you already know, and I see here we have some of the regular users. We have a free of charge Sanger sequencing service for all our partners. So if you're interested to run Sanger sequencing, you're welcome to contact us. The only thing you need in your lab is a conventional PCR. You can run the conventional PCR, and the amplicon you can send via our free of charge Sanger sequencing service, and you can clarify such issues. Yeah. So that's, and again, another information, in a few weeks' time, we are planning to organize a training course, virtual again, unfortunately, on the use of the Sanger sequencing service. So please be prepared if you're interested to join that course and learn how the system works. There are there is a workflow which is already established and very well used by many laboratories, but people need to learn the whole workflow. So it's not so, it is simple, but it is not too simple to go just straight forward. You need some training to understand the sequencing service. Thank you.
Thank you, Ivancho. Thank you, Dan, and other experts for a very clear explanation. One of our participants asked for a comment on the specificity and sensitivity of RT-qPCR regarding SARS-CoV-2 detection. So, if someone could comment.
Okay, there are for SARS-CoV-2 there are several recognized and validated assays, and it's always good to have one that is routinely used for screening and another one that is used for confirmation. Preferably, the alternative one should target different genetic region on the SARS-CoV virus, but more or less the diagnostic of SARS-CoV virus is very well established, and I don't think we need to waste a lot of time. So it's the matter only of internal verification and startup of the assay in the internal laboratory. Thank you.
Thank you.
Yeah, I would just short comment that, yeah, as Ivancho said, that there are still I'm not aware of any reported changes in the assays originally, let's say, published for detection for screening in the N-gene or the E-gene. So usually you should use, let's say, at least 2 targets in your PCR to increase your specificity as well as the sensitivity. But specificity, there is no problem with that, and specificity would be affected as for all other PCR assays, let's say, from the sample, but taking into account that the sample, the oropharyngeal or nasal swab doesn't have much inhibitors, shouldn't be a problem, but it will be depend only on the viral load and on the phase of and of course the technique how the sample was taken. So so no, not much more about that topic.
Thank you, Igor. Next question from Sudan. For nested PCR, can I use human infected positive samples as positive control to detect the same gene in the animal samples? Yeah, please comment someone.
I think we should need more information about the assay and the targets. So if the target is the same for human and for the animal, it doesn't matter if it's human or animal, because it's only what matters. It's only the sequence you want to amplify. So if the sequence is the same, then you can use the material from human as a control, and then.
Yeah, thank you. Next question from Jennifer Maravilla. In countries where virus isolation is not available, is it recommended to do confirmation of an outbreak using second verified real-time PCR assay that OIE recommended? Someone, please.
Well, I think the question is not the second one, but 2 verified real-time PCR assays. Well, we know that not every virus could be isolated anyway. There are some viruses that they still could not be cultivated in vitro. So taking that into consideration, definitely if these 2 real-time PCR methods are validated, and if both of them are verified in your laboratory, then yes, you can declare the outbreak if these 2 are definitely positive.
I would just like to add that not only a second, let's say, if your screening is based on a real-time PCR and you find a positive reactor, positive sample, then the confirmation doesn't have to be confirmed by a second real-time PCR. It can also be confirmed by another validated conventional PCR as well, if of course the amount of analyte is sufficient and it is within the range of the operating range and the limit of detection of the conventional PCR. It just have to be confirmed at least with 2 different antigen assays. I think it would be sufficient to confirm, let's say, the outbreak.
Thank you, Igor. The next question is probably for Ivancho. I am not a veterinarian, but I want to take part in Sanger sequencing training. What must I do?
So, yeah. I mean, okay, if the person is not veterinarian, but working for a veterinary laboratory, you can still submit samples. But the eligible partners in this Sanger sequencing service are the official veterinary laboratories from our counterpart community. So we don't offer the service out of the veterinary network. Let's say, I'm sorry for that if it's some other laboratory, but I don't understand. Is the person not veterinarian working for a veterinary laboratory, or it's a non-veterinarian working in non-veterinarian lab? So unfortunately for non-veterinary labs, we do not offer this service.
Thank you. Thank you, Ivancha. Again, question from Kamilika. Can you explain, please, any technique to improve the DNA and RNA quality and yield during extracting process? Very technical question. So maybe
yes, as you said, it's very technical question, and it depends on the. It can be different kits, different extraction kits, which will have different performances. Also depends on the pathogen which you want to isolate. Is it the virus? Is the DNA virus or RNA virus? Is the bacteria? What kind of matrix you use for the extraction? And of course, it will in a degree, let's say, be influenced by the technique of the operators, of the technicians. And at the end, here is the if there is a possibility, of course, to use automatic extraction, which is probably the best way to increase the quality as well as the yield of the DNA or the RNA. So yeah, it's a very technical question, and of course, beside the technique of performance, it's mostly up to the performance of the extraction kit used.
Thank you, Igor.
Thank you. One transition. I'm sorry. So if you're suspecting sample with a very low DNA or RNA quantity, there are special extraction kits for special situations, for ultra high efficiency in the extraction, but they are much more expensive than the normal ones. So one example can be the so-called forensic kit for DNA and RNA extraction. It is something like 3 to 4 times more expensive than the normal ones, but it yields the same proportion, maybe 5 times more DNA, RNA from the samples. So we used it for extraction of DNA from lost environmental feather samples from the keratinous tissues, and they work very well, but they are extremely expensive. So if you have suspicious case with enormous small amount of sample and you need to extract it, then it's a special kit to use.
Thank you, Ivancha. And we have this question, but I think Ivancha have just answered it. What could you advise for low-level viremic samples, RNA viruses, yielding detection with RT-PCR? But Ivancha gave a very good reply now. I should ask audience if we have more questions. Not so far, but you are welcome to submit and to join our training again tomorrow. I think for now we finished, and I would like to thank our experts for fruitful discussion and our trainees, participants for participation in our training. And tomorrow morning we all expect you to join our training again. Thank you very much for attendance. See you tomorrow.
See you tomorrow.